welcome to the next lecture and chapter, and that is attributed to the introduction to source models. So in this particular chapter, we will discuss different source models. They are applicable for the process safety and how we can derive the various equations applicable to these source models. We can perform the modeling. Let's have an introduction of these source models. We all agree that the chemical process industries are usually prone to accidents, especially fire, explosion, different type of toxic release, etc. And these incidents or these accidents, they are attributed to the variety of reasons, maybe human, maybe equipment failure, maybe some other things. So usually small incidents progressively result to a big accident which costs towards the loss of man, material and money. And everywhere when we talk about in terms of economics, everywhere there is a loss of money or economics, because if any incident takes place towards the man, maybe fatality or maybe injury or maybe illness, you need to pay the compensation. You have to take care of that particular human being. If there is a loss of a material, then again there is an economic loss. So sometimes we need to take care of those small incidents which may cause a severe problem. Now, especially when we are considering the material, because all these source models are attributed to the material and the process. So these materials which may be released or which may cause a severe problem, they may be highly toxic, they may have a high calorific value. These two possibilities are there. There may be some common incidents that may include maybe sometimes rupture or break in pipeline. This may cause the exposure or evolution of any kind of toxic material to the atmosphere, or any kind of flammable material may get discharged into the atmosphere, form the flammable vapor cloud, etc. Sometimes hole in a tank or a pipe may create a problem. It's not only attributed to the flammability aspect or a fire and explosion aspect or a toxic release. Sometimes this leakage may create the economic losses because the material will get destroyed. There may be a chances of a runaway reaction or a fire extended to the vessel. And these runaway reactions sometimes because of the failure of any kind of sensor, because maybe sometimes of a human involvement, these thermal runaway reaction or chemical runaway reaction may take place, and it may create a problem to the plant. So source models, they are used to describe the discharge of the material due to the incident from the process. This is the basic methodology of all these source models. The source model provides a description of mass or volumetric flow of discharge, the total quantity of discharge, because sometimes you need this information to assess the safety aspect of your process or your equipment. Phases of discharge material may be solid, liquid, vapor, or sometimes multi-phase. So this is again a very crucial issue. So these type of description is necessary for source model description. The total time for the complete discharge. This is again a very crucial aspect. How much time is required to empty the vessel or empty the pipeline, etc. The fundamental or empirical equations are used to define the source model, and each incident has its own or unique model. Now let us have a look of these incidents. There are variety of incidents listed in this block. That is a selection of release incident, sometimes rupture or breakage in pipeline, sometimes a hole in a tank or a vessel or a pipeline. Flashing may create a problem, means from high pressure zone to the low pressure zone, it may create a problem. Sometimes runaway reaction may cause a problem. Sometimes maybe the fire exposure creates a problem. and others which may be enlisted in several aspects. So while you have selection of a release incident, then you select the source model. The prima facie, the requirement is the model must fit the release incident. So by this particular aspect, there are certain outcome. The total quantity released, you can easily find out. The time of complete discharge, the mass or volumetric release rate, and the material phase. So whenever you have carried out this one, then go for the selection of dispersion model. Mostly this selection of dispersion model is done for the toxic release, and sometimes influencing factors are what are the wind speed. So while if you go to the Bhopal gas tragedy, the wind speed was a crucial aspect for all those fatality. What is the temperature inversion? That has to be looked into. Buoyancy effect, because sometimes the density difference may create problems. Now the results may include the downwind concentration. You may have you may have a clue about the area affected and the duration. Then while we considering the flammable or toxic substances, we can enlist two different type of scenarios. So let us have a look of the flammable aspect. Then the selection for the fire and explosion model, you may have a look of the TNT equivalency, trinitrotoluene equivalency model, TNO multi-energy models, multi-energy explosion, there may be a chances of fireball, then Baker-Stirhole the tank model, then different other models. The result may include the blast over pressure and the radiant heat flux. So if we consider the flammable and toxic both are toxic, then effective model response versus dose, we have already discussed this in the toxicological studies, the Probert model, the log uniform model, and others. The result may include the toxic responses and number of individual, what are the quantity of individual affected, and the property damage. Usually the property damage in case of toxic studies are bit minimum compared to the flammability aspect. Now there are certain mitigation factors like distance between the possible release points, escape plan or shelter aspect, secondary containment for storage, handling in a fire situation, the remote shut-off flow limitations, absorbent foam, other covers, water spray or steam curtains, etc. So these are the certain scenarios. Then we go for the consequence modeling. After when we carry out this thing, then we can go ahead for the consequence modeling. So while we consider the safe modeling, the result obtained from source model will not define the whole event completely. Now if the physical properties of the fluid discharge cannot be characterized and the physical process involved cannot be understood. So if any kind of uncertainty exists, the parameters should be selected to maximize the release rate and quantity. Now this ensures the design is on the safe side. Now safe design requires for certain things like choose conditions for maximum release rate, the maximum quantity, and if uncertainty exists, choose the worst scenario. It is just like that if you wish to design the things, you may take the LPG cylinder, domestic LPG cylinder, and you take the maximum quality that the cylinder is completely filled, 14.2 or 14.5 kilogram as applicable to the cylinder. Now worst scenario is that the cylinder will burst and all the entire LPG will escape from the cylinder and it will catch the fire. So this is the worst scenario. So while we consider the release modes, so there are wide aperture release, and you can have a look of this particular figure. Explosion in a storage tank. This is your storage tank, and this explosion is mainly attributed to the overpressure. Now there are certain limited aperture release. There may be a hole in the tank or there may be chance of a crack in the tank, or sometimes the crack may be in the pipes. Sometimes leakage in the flanges. There is the hole, and there may be a leak in the flanges. Sometimes leak maybe through the pumps. Sometimes there is a scenario of a broken pipeline. So there are different release modes in this particular pressure vessel or a storage tank. Now, while considering the basic source model, there are 7 things which we need to know. That is the flow of liquid through a hole, because if you consider the previous one, what is the flow of a liquid through a hole, and consider this scenario is a bit different from the scenario at this point. Then flow of liquid through a hole in a tank, flow of liquid through pipes, flow of vapor through holes, flow of gases through pipes, flashing liquid, and a liquid pool evaporation or boiling. Now let us consider first thing, that is the flow of liquid through a hole. So basically this particular thing is attributed to the mechanical energy balance equation, which describes the various energy forms associated with the flowing fluids. So this is the basic mechanical engineering equation, mechanical energy balance equation. dP upon rho, integration of this, minus bar u square upon 2 alpha gc plus g upon gc delta z plus f minus w upon bar, where P is pressure in the force per area unit, rho is the fluid density, the mass per unit volume. So, and U bar is the average instantaneous velocity of the fluid, instantaneous velocity of the fluid, length per time. Gc is the gravitational constant, that is length mass per force time square. Alpha is the unitless velocity profile correction factor, unitless velocity profile correction factor. Usually alpha is having the value of 0.5 for a laminar flow, 0.05 for laminar flow, and 1.0 for plug flow. It tends to 1.0 for turbulent flow. Now G is the acceleration due to gravity, having the units in terms of length time square. Z is the height above datum in length unit. Ws is the shaft work, that is the force length. F is the net frictional loss term, that is length force upon the mass, and M is the mass flow rate, that is mass per unit time. For incompressible liquid, the density is constant, so we may keep this formula like this. And the frictional losses in the leak are approximated by a constant discharge coefficient CD. CD is the constant discharge coefficient. So the equation is coming out to be delta P upon rho minus F is equal to CD square delta P upon rho. It is just like this after applying all these assumptions. So the average average discharge velocity from leak can be determined as U is equal to CD under root alpha twice GC upon this, like this. Now if we take C naught is equal to CD alpha, then bar U is equal to C naught twice GC G upon rho. So this is after certain derivation, then the mass flow rate Qm will be the mass flow rate Qm is equal to rho U A is equal to A C naught twice rho GC PG. So the total mass of liquid spilled depend on the total time that leak is active. So C naught is equal to F RE. RE stands for Reynolds number. D. Now D is the diameter of the hole. Now for sharp edges, and usually this happens for sharp edges and Reynolds number is greater than 30,000. So C naught tends to 0.61. The exit velocity of fluid is independent of size of the hole. So now various values of discharge coefficient, we may list these various different values of discharge coefficient. So for well rounded nozzle, C naught tends to 1. For short sections of pipe, L by D is greater than 3, length upon diameter, attached to the vessel, which we have previously discussed and shown in the slide, to a vessel, C naught is almost 0.81. So you may use C naught is equal to 1 for unknown or uncertain values. For a safer side. Now let us take another aspect, that is a flow of liquid through a hole in a tank. Flow of liquid through a hole in a tank. Now this is the tank, like this. You are having certain liquid is filled over here and you are having a hole at this juncture. So you may have a different profiles like this, and this is the height of a liquid HL, the pressure exerted PG, initial is 0, WS is 0, and U2 at this juncture is, let us say, U, and P is equal to 1 atmosphere because it is exposed to atmosphere. So Qm is equal to rho AC naught to Gc G upon rho plus GHL, like this. Rho is the density of the liquid and A is the leak cross section area. So, and usually your usual physics phenomena applies over here. So, usually, so whenever if you have a hole develop, because it's a very common practice, so a hole develop in a tank at a height HL below the fluid level. This is your initial fluid level, because when this hole is developed, this fluid level will deplete. So, a flow of liquid through this hole represented by a mechanical energy equation or a mechanical energy balance equation, and you may take one assumption that liquid is incompressible in all aspect. So, the mechanical energy balance equation is dP upon rho plus delta bar u square upon 2 alpha Gc plus G upon Gc delta Z plus F is equal to minus Ws upon mass flow rate minus delta P upon rho is equal to delta P. We have taken this assumptions previously. So, the assumptions what we have taken, that is Pg is the gauge pressure on the tank. I am again redrawing the tank figure over here. Here is the hole. So, hole. This is the liquid level. This is HL. Now, external gauge pressure is equal to atmospheric pressure. The shaft work Ws is equal to 0, and the velocity of the fluid in the tank is equal to 0. So, discharge coefficient CD can be determined as delta P upon rho minus G upon Gc delta Z minus F is equal to CD square minus delta P upon rho minus G upon Gc delta Z. Now, if we solve this equation for getting the average instantaneous distance velocity from the leak, that is u, is carried out by this formula. GHL. Now, if we say that if C naught is equal to CD square root of alpha, then U is equal to C naught to Gc Pg upon rho plus GHL. So, therefore, the instantaneous mass flow rate will be given as Qm is equal to rho AC naught to Gc G upon rho plus GHL, through which you can assess the instantaneous mass flow rate. This is instantaneous mass flow rate. Now, as the tank empties, the liquid height decreases and the velocity and mass flow rate decreases. Now, if the vessel was filled out with an inert gas to prevent the explosion or was vented to the atmosphere, Then the gauge pressure P, P on the surface of the liquid is constant. So for a tank constant cross-sectional area is having the AT, the total mass of liquid in the tank above leak is M is equal to rho AT HL. So this is the total mass of liquid, in the tank above the leak. That is like this. You are having this, you are having the leak over here. So this is the total mass. Now let us have a look of rate of discharge, rate of change of mass. So this is always having the time factor. So dm by dt is equal to minus qm. Now if we combine all the equations and integrate, then you will find that HL is equal to HL naught at t is equal to 0, and HL is equal to HL at t is equal to t. So we can find out the liquid height level in the tank. So HL is equal to HL naught minus C naught A AT 2 GC PG upon rho plus 2 GH L naught T plus G by 2 C naught A upon AT T the whole square. So mass discharge rate at any time t is given by Qm is equal to rho AC naught twice GCPG upon rho plus G H L naught minus rho G C naught square A square, this is A, upon AT T. So by this equation you can calculate the mass discharge rate at any time t. Now let's have a look about the time for emptying the tank. This is again one of the thing which we need to discuss. How much time required to empty the tank? Again, let us have this tank in question. Now here you are having the leak like this. This is the HL, U1 naught is equal to 0, WS is equal to shaft work is equal to 0. Now this is the tank. Now time for vessel to empty to the level of the leak you can determine by TE. This is the TE is the time to empty the tank, is equal to 1 upon C naught G AT upon A twice GCPG upon rho plus G HL naught minus under root of twice GCPG upon rho. Now if vessel is at atmospheric pressure, then PG is equal to 0. Then TE is equal to 1 upon C naught G AT upon A 2G HL naught. Now let us consider another thing, that is the flow of liquid through pipes. Now here is a pipe like this, which is having the length L, Rho, let us take that rho is constant. Through pipes. Now, initial conditions are P1, U1, Z1, and the final conditions are P2, which is less than P1, U2 is equal to U1, and Z2. Here we have taken this thing that rho is constant. Now, let us say that pipe transporting liquid is shown in the figure. The liquid flows through the pipe due to the pressure gradient across the end of pipe. Now, there will be a definite amount of loss in pressure encountered due to the presence of frictional forces between the liquid as well as between the fluid and the wall of container. So, losses due to friction in long pipe are quite larger than the losses due to the bent and sudden enlargement and contraction in the fitting. So, for incompressible fluid, the mechanical energy equation can be written as delta P upon rho plus delta U bar U square upon 2 alpha GC plus G upon GC delta Z plus F mass flow rate. Now, frictional loss term F, this is the frictional loss term. This includes the loss due to the flow through length of pipe. Fittings such as various kind of fittings may take place like control valves, bends, sometimes orifice, etc. Pipe entrances and exit. There may be sudden expansion and contraction across the pipe. So, there are so many things related to this one. So, we may calculate the friction loss F, like F is equal to Kf U square upon 2 Gc, where Kf is the excess head loss due to pipe or pipe fittings. This is usually a dimensionless, and U is the fluid velocity, and Gc is of course our gravitational constant. So, excess head loss you can calculate through this particular equation, that is Kf is equal to 4 Fl divided by D. F is the fanning friction factor, which is of course unitless. L is the flow path length, that is having the unit of length, and D is the flow path diameter having the unit of length. So, for a laminar flow, the fanning friction factor is given by F is equal to 16 by R. R is the Reynolds number, that is for the laminar flow regime. And for the turbulent flow, it is given as minus 3.7 d epsilon plus 1.255 upon RE F. This is for the turbulent flow. So, 1 upon RE is equal to the power minus 0.25 upon square root of F minus 1 upon 3.7 d epsilon. Now in this particular table, you can have a look of various roughness factors epsilon for clean pipe. So in this particular table, we have enlisted different type of pipe materials with different roughness factors, like riveted steel. It is having the roughness factor of 1 to 10 mm, concrete 0.323, cast iron 0.26, galvanized iron 0.15, commercial steel 0.046, wrought iron 0.046, drawn tubing 0.0015. In glass, the roughness factor is 0, and the plastic, the roughness factor is 0. Now here is the Moody's diagram, which tells you about this is a depiction of relative roughness factor epsilon by D with respect to the Reynolds number, that is Re U upon D, with the friction factor F. So you can have different, you can calculate or you can find out based on your material in question. Then you can find out the friction factor either with the help of a Reynolds number and relative roughness with the different zones like laminar, critical zone, transition zones. So you can easily find out the things which you may require in due course of time for calculating the friction factors. Now in the next aspect, we are going to discuss the for the fully developed flow, that is F use for fully developed flow, the F is independent of Reynolds number. So 1 upon under root F is equal to 4 log of 1 upon 3.7 D upon epsilon. Now if we take the smooth pipe, which we have enlisted previously, so for a smooth pipe, epsilon is equal to 0. So 1 upon square root of F is equal to 4 log Re square upon 1.255. Take the help of the previous slides. Now we may take the Blasius approximation. For this Blasius approximation, you can refer the references. So for the smooth pipe with the Reynolds number less than 1 lakh, F is equal to 0.079 Re to the power 1 by 4. Now while considering the flow of liquid through pipes, let us take the 2K or Hooper model. Now it is possible to calculate the loss in pressure head for pipe fitting, valve, orifice and other flow obstructions. This is the method applies for this one. The calculation of losses due to the pipe friction is not possible through these methods because they have a very long length of even in kilometers, and the friction factor is a function of a pipe length. So in 2K model defines the excess head loss in terms of two constant, that is the Reynolds number and the pipe internal diameter. So when we have this particular aspect in consideration, then we may have this Kf is equal to K1 upon Re plus K naught, small k naught infinity, K infinity 1 plus 1 upon I d inches. Now head loss Hi through the fitting can be calculated by the determining the value of Kf from this equation and using it to this equation, that is HL is equal to Kf V square upon 2G. Now head loss through pipe friction, which you can calculate by HF, is equal to F LV square upon D to G. So the total head loss would be HT is equal to HF plus HL. Now if we apply the 3K Darby method, so in this method Kf is equal to K1 Re plus K infinity 1 plus Kd inches. Now here Kf is the excess head loss, K1 and K infinity they are constant, Id is the inside diameter which is in inches, OD is the outside diameter in inches. So you can calculate this Kf by this method. Now in the next table, this one, we have enlisted the constant for 2K methods for loss coefficient in fittings and valves. So there are multiple type of fittings like elbow, which is having the 90-degree angle, and description of fitting that it is standard R by D is equal to 1 threaded, and K1 is 800 and K infinity is 0.040. Long radius R by D equal to 1, flanged or welded 800 and 0.25. Long radius, that is R by D, equal to 1.5, and all types of things are clubbed under this head. So K1 is equal to 800 and 0.20 is K infinity. Similarly for elbow, which has metered at R by D equal to 1.5, one weld 90 degree, 1000, 1.15, two welds 45 degree, it is 800 or K infinity is 0.35, three welds 30 degree, 800, 0.30 K infinity, four welds 22.5 degree, and that is 800 and 0.25, and 5 welds 18 degree, that is 800 is K1 and 0.25 is K naught. Similarly, if we have 45-degree elbow, that is standard R by D is equal to 1 for all types. K1 is 500 and K infinity is 0.20. Long radius, we may have certain things related to the long radius. R by D is equal to 1.5. So 500 is K1 and 0.15 is K infinity. Then 180-degree elbow, the standard R by D is equal to 1, may be threaded. So 1000 is the K1 and 0.60 is K infinity. Similarly, standard R by D equal to 1, that is flanged or welded, that is 1000 and 0.35 is the K infinity. And long radius for all types, that is R by D is equal to 1.5, K1 is 1000 and 0.30 is K infinity. There are various T's. T's are like this, sometimes used as elbow. The standard threaded, maybe long radius, maybe threaded, standard, flanged or welded. So they are having the respective range of K1, K infinity like 500 to K, and K infinity is 0.70, then 800 is the K1 and 0.40 is the K infinity, and 800 is standard flanged or welded. For this we are having the 800 is K1 and K infinity is 0.80. Similarly, sometimes fittings they are used as a elbow, that is a stub in branch. So K1 is for them, the K1 is 1000 and K infinity is 1.0. Sometimes there are certain run-through fittings, they are threaded 200.1, flanged or welded 150.5, stub in branch they may be 100 and none. Sometimes valves may be gate valve or a plug. The full length size beta is equal to 1.0 and the K1 is 300 and K infinity is 0.1. Reduced trim 500 and 0.15. Reduced trim beta is equal to 0.8. For this the K1 is 1000 and K infinity is 0.25. Then there are certain fittings related to the globe. Then the standard, for the standard the K1 is 1500 and K infinity is 4. Then angle or gamma type, then K1 is equal to 1000 and K infinity is 2. There are diaphragm and butterfly. The dam type of description of the fitting is dam type. Then for this 1000 to 2 is infinite, K infinity 800 and K infinity is 0.25. Check valve may be lift 2010, swing 1500 1.5 and tilting disc 1000 to and K infinity is 0.5. Now this particular table enlisted the constants for 3K method of loss for loss coefficient in fitting, and you can have a look of all kind of 90-degree elbow, that is threaded, long radius, flanged, etc., and their respective values in terms of K1, K infinity and KD. So for your reference you can always use this particular aspect, and here in this particular table the 45-degree elbow is enlisted with respect to the K1, K infinity and KD, standard, long radius, etc., threaded, flanged and different descriptions likewise. In this particular table you can have a look of different type of T's like standard, long radius, etc., and their respective K1, K infinity and KD values. Now in this slide we have the different valves like angle valve, globe valve, plug valve, gate valve, ball valve, butterfly valve, swing valve, lift check valve, and the values of K1, K infinity and KD. So in this module we have discussed different aspects of source model, and especially applicable for the liquid and liquid system. So we have discussed the flow of liquid through a small hole, cracks, etc. And in case of further referencing, you can have a look of various references which are listed in this particular slides, and hopefully this particular information is useful for you. Thank you very much.